All right. So today is Friday. So we are learning about free fall and gravity. So we're going to talk about kind of the forces here, and then kind of discuss what it has to do with a lot of things regarding us on Earth, and then also just kind of looking at Newton's laws, stuff like that, and then talking about different cool examples. So should be a pretty cool day. But yeah, let's start with looking at actually forces and gravity too. So let's start that.
Some people say there's no gravity in space. Well,
Right.
what pulls our Earth close to the sun, and what makes asteroids hit Earth?
Great
Gravity.
question. Yeah, exactly. So there's gravity. So technically there's always gravity force between all things in the universe, but they're too small
And
to actually make a difference, right?
and weight is actually how much effect gravity has on you.
Right. So we'll definitely talk
And
about that.
and the more mass you have, the more gravitational pull you exert.
Very
Everybody
true.
on Earth exerts a gravitational pull. If you have more mass than Earth, you'll pull Earth, which is kind of weird.
Right, exactly. So today we'll talk about falling objects and gravity. So everything that you kind of already mentioned, Ray Chan. We'll
Any
talk about
Newton's law. Anything
exactly Newton's
that's
laws.
moving will keep on moving unless an unbalanced force acts on it.
Exactly. And we'll talk about that today in more detail. So cool. Oh, I'm not sure what just happened. Oh, there it is.
Screen.exe has stopped working.
Okay. Do you see my screen?
Yeah.
Still sharing? Okay. So yeah. So here we're looking at actually how. Let's talk
Wait, I
about
know
first.
the answer to the first question.
Yeah, exactly. So
As,
let's
like
talk
when they
about
reach
first fall.
terminal velocity, like before they reach terminal velocity, they always get faster. But after they reach terminal velocity, they can't go any faster.
Yeah, so we'll talk about terminal velocity too. Usually in kind of our introduction to physics topics, we really don't like to consider air resistance or anything that kind of that we can't really simulate very easily. So air resistance is harder to calculate. So usually, let's say there is no air resistance, and we like to use that example all the time. When things are falling, let's say in a vacuum, right? We talked about a vacuum.
Vacuum is
Gotcha.
an area where there's no like things.
Exactly. There's nothing in there. So let's say if something's falling in a vacuum, so that means that it'll keep on going faster until it hits the ground, basically. So that's actually a really cool thing to think about, and we'll talk about what the importance of that is later on. Do objects with different weight fall at different speeds? So this is a really weird question. And again, let's talk about it. Let's say we have a bowling ball and a piece of paper falling in a vacuum. What do we
A
think
bony
is
ball will
going to
fall
happen?
fast. Wait, they'll fall at the same rate because there's no gravity.
Well,
Well, if
there is gravity, but
okay,
there's no
then
air
the bony ball
resistance.
will fall first. No, we'll reach the ground first.
Okay, what do you think, Hao-chan?
I agree.
You think the bowling ball will hit the ground first? So
Yeah.
that's yeah, and we'll talk about actually what happens later on. But again, if we have a bowling ball and a piece of paper falling in a vacuum, right? Basically, like say a giant box with no air in it, still on Earth. So that means it's still being pulled down from Earth's gravity. But that means that there's no air inside of that vacuum, which means that air resistance isn't going to slow down either of these objects. And we'll see what happens because of that. And what causes things to fall? What causes anything to fall? Gravity. So free fall is all about gravity in this case, and we'll talk about gravity later on more.
An unbalanced force.
Unbalanced forces is what causes things to speed up, right? So basically two huge physics definitions that we need to establish before we can move on is talk about speed and acceleration. So speed is basically how fast you're going, right? How much distance you're covering per second, let's say, or per minute. That gives you a speed. Let's say like how fast you're running, for
It's
example.
measured in meters per second.
Meters per second is it the most commonly
Acceleration
used?
is measured in meters per second times 2.
Yeah, per second squared, basically. So yeah, so let's say your speed. Do you know how fast you can run? Probably. Let's say a mile.
So you can run at 18 meters per second, which is definitely not real.
18 meters per second. Well, actually, 18 feet per, 18 miles per hour is actually pretty reasonable, like for like an adult runner, 18 meters per, miles per hour. Sounds pretty reasonable. But okay, so have you guys ever ran a mile before?
Yeah, I once ran 5 miles
Really? That's a lot.
non-stop.
Actually, let's use swimming. Swimming is probably the most, applicable for you guys, right? So,
Yeah.
what distance do you want to use?
What?
What distance do you want to use for swimming?
100 meter.
100 meter what?
100 meter freestyle.
100 meter freestyle. What's your guys' best time for 100
My best
meters?
time is 1:11.
1 minute and 11 seconds.
Yeah, that's very fast for a kid like him.
So 100 meter freestyle, 1 minute 11 seconds. So basically, let's calculate the average speed that Hao Chen is running. Swimming for that 100 meters. So 1 minute and 11 seconds. So how many total seconds is that?
What do you mean?
So 1 minute is how many seconds?
1 minute is 60 seconds. So
Yeah,
that's
and
71 seconds. 71
Yeah, so
seconds.
in total, he is swimming for 71 seconds. And we said that he is swimming 100 meters. So 100 meters in 71 seconds, well, that gets you, I have to put down a calculator, but
Use Google.
true. Use Google. Gets you 1.41 meters per second. That's his average speed when he's swimming, is 1.41 meters per second. So do we see how that's a speed, right?
Yeah.
Acceleration, on the other hand, is how much that speed is changing per unit of time. So that's why instead of meters per second, the unit here is meters per second per second. So basically meters per second squared, or meters per second times second. And basically, I think the best example is you're in a car, right? And you're at a red light. And once it turns green, what is your parents doing to the car? They're accelerating it, right? Basically, because they're going from 0 to a speed, let's say 60 miles per hour or 40 miles per hour. They're going from 0 to 40, which means the speed is changing. Now, let's say you're going 40 miles per hour on a highway constantly. Are you accelerating?
If you're going on a high, like what?
Let's say you're going a constant speed on a highway. Does that
You're
mean
not
you're
accelerating? You're not accelerating.
Yeah, you're not accelerating. And basically, let's say you close your eyes in the car, right? You're sleeping on a highway, in a car on a highway going 60 miles per hour. You wouldn't actually even know that you're going 60 miles per hour.
Yeah, you're actually going 60 miles per hour. That's why seatbelts are so important.
Right. But like the thing is, you wouldn't feel that you're going 60 miles per hour, right? We can't feel how fast we're going. I mean, like, for example, we're on Earth right now, right? Is the Earth accelerating? Or is it moving basically like we won't be able to feel that the Earth is going millions of miles
until the Earth actually stops.
Yeah, and then we'll feel that acceleration. So
and then we'll be like flinged out of our seats and die.
Yeah. So same thing like on a train or anything like that. If you're going a constant speed, you won't be able to feel that you're going a constant speed because, well, there's no force acting upon you. If there's an acceleration, though, that means there's a force acting upon you, then you'll feel that acceleration. So that's probably the best example I could give you. Does that make sense?
Yeah.
Both of you guys? Yeah.
Yeah.
Okay, cool. So yeah, speed and acceleration. Speed is how fast you're going. Acceleration is how much that speed is changing per that same exact time. So speed, for example, we already gave a few, right? Is airplane, right? On an airplane, you're going, once you're in the air, you're going a constant speed, right?
Yeah.
Have you guys been on an airplane? I'm assuming.
Yeah.
Yeah. So when you're taking off, though, you could feel that like your stomach is dropping, right? Like you feel that feeling in your stomach, and you're being pushed into your seat, and that's because the plane is accelerating from basically 0 to, let's say, 500 miles per hour. So it's going from 0 to 500. That's accelerating. But once it hits that 500 and it keeps on going 500, that means it's not accelerating anymore. It's just keeping constant speed. So this all has to do with forces because, well, we'll learn about that later on. But forces is basically anything that pushes or pulls on an object. So if you open a door, you apply a force. You're walking, you're applying a force. Basically anything that causes an object to accelerate or to move or changing speed, that's a force. So there's a lot of different types of forces out there. Could either of you guys give an example of a force?
Um. Rocket booster.
Yeah, a rocket. I mean, is a force. What about you, Hachan? You want to give an example of a force?
Propellers.
Propellers for, let's say, a plane
Ship.
or a ship. All of those are forces. Awesome. Is gravity force? Yes. Gravity is definitely a force that causes things to fall, right? Or at least pull us to the surface. So those are all forces. Can you name any other forces? So let's think about other types of things, not necessarily things that, just push or pull physically, but could you guys name any other forces?
Um. Hmm. Lift.
Yeah, you're lifting something, that's force. But let's say like I don't know exactly what to say here, but like like electricity is also part of a force. Because in an electrical field, things can move, right? Charged things can move. So a magnet, right? A magnet is a force, magnetic forces. So magnets, how do magnets stick to your refrigerator, for example? That's a force. Because if the magnet wasn't sticking to the fridge, it would have fallen to the ground, right? Because of gravity. So that's a force. Other forces, electricity, magnetism, gravity, all of those push forces that we talked about, or pull forces. There's more, but yeah, nuclear bombs. So those are also forces. But okay, Newton's laws. So basically, Isaac Newton was kind of credited to founding kind of modern physics that we talk about, classic physics of motion, stuff like that. And he made laws regarding these motions of objects. So does anyone know the Newton's first law of motion? I think Rachel actually said it before. So the first law of physics is an object at rest will remain at rest unless acted on by an unbalanced force. An object in motion will continue to be in motion at that constant speed and direction unless acted on by an unbalanced force. So this is saying a lot here, and let's kind of unravel this a little bit. That means your water bottle on the table will stay there until someone acts upon it, right? Or a satellite. Do you guys know the Voyagers? Voyager 1, for example. Voyager 1 is a thing in space that is moving very far, far away from us. It's a satellite that's carrying some, cool equipment. But this is moving away from us, right? It's moving at, let's say, 1,000 miles per hour. It's going pretty fast away from us, but it just keeps on moving. Does that mean that it will keep on moving, or will it slow down over time? And this is a weird question. So will
It'll
this
slow
slow
down
down over
over
time?
time. It'll slow down.
What?
Slow down over time.
What will slow it down?
The fuel will dissipate.
See, the thing is, though, is that let's look at Newton's first law again. It says an object in motion will continue to be in motion unless acted on by an unbalanced force. So in space, there really are no forces acting upon this satellite. There's no air slowing it down. There's no gravity pulling it away because, well, there is gravity, but it's too small to make a big impact, which means that actually, once it reaches a certain speed, it will keep on going that certain speed forever, basically. It will just keep on moving away. Just like and it's that's a really weird concept, right? You think it would slow down. I mean, on Earth it would slow down because there's air on Earth slowing it down, right? Basically pushing against it. But in space there is no air because, well, there is no air, so nothing will slow it down
But what if
until
it
it
crashes
basically
into a
crashes.
star? What if it
Yeah,
crashes into a
unless it
star?
crashes into something or something like that. But you gotta realize that in space, 99.9% of the universe is empty space. So the probability of it actually crashing into something is pretty low, at least for now.
But 1% is a lot
True.
for
Over
the
time, it'll
universe.
probably crash into something, but not in the next, 1,000 years or millions of years. So, um, and it's basically sending us cool information and satellite images and stuff like that. But the point here to note is that an object will stay in motion. This is the one that most people don't understand really, is an object will stay in motion until something acts upon it, right? Like a soccer
Mm-hmm.
ball. I kick it, it will keep on going up. Well, it won't keep on going. Well, let's say I'm on a flat surface. I kick a soccer ball, it won't stop until it hits a net, or basically it's going to slow down, right? And why is the soccer ball going to slow down on Earth?
Because there's a medium.
Yeah, there's air slowing it down. Let's say if it's on the ground rolling, there's friction. Do you guys know what friction is?
Yeah.
Friction is basically a force that slows things down because they're rubbing against each other. So in the case of a soccer ball is rubbing against the floor, right? So it's slowing down. But let's say there was no friction and there was no air resistance and I kicked the ball on Earth. That means that ball will keep on rolling at that same speed for infinity, for forever, basically. But we know that's not true because on Earth we have friction, we have um, air slowing it down, stuff like that. It's not to say that in space there is no friction, right? If two things rubbed against each other in space, that would still be friction. But, well, in the case of the Voyager, there's nothing rubbing against it, so it would keep on going forever and forever and forever. So that's Newton's first law. And again, an object at rest will stay at rest unless acted upon by an outside force. And that's why meteors in space, for whatever reason why they started moving in the first place, let's say it was a big explosion, um, those meteors are going to go in that same direction forever until it hits into something or gets subjected by something, let's say gravity, right? Gravity's going to pull in the meteor. So those are things we have to consider for Newton's first law. Does that make sense? Any questions on that?
No.
Cool. Newton's second law. Oh, sorry. So this is kind of something called inertia. Inertia is also another thing that we can use in this case. is basically just an object's ability to resist a change in motion. So the larger the mass, the larger the inertia. So basically, I kick a soccer ball or I kick a giant rock. Which one has a larger inertia?
Or giant rock?
Yeah, a huge rock, a boulder. Which one has more inertia?
Well, how much energy would you have, like, if you would need to kick a rock?
Well, in the case that I'll definitely not be able to kick that boulder, I can kick a soccer ball though, right? And in the first point, it says inertia, the larger the mass, the larger the inertia. And mass is basically how heavy something is, let's say for now. Basically just the amount of matter inside of it, right? So basically we know that a rock has more mass than a soccer ball, right? It's so much more heavier, this giant boulder. So that giant boulder won't move if I kick it, right? Because it has such a large inertia, it resists my force to change its motion pretty well. In the case of a soccer ball has much less mass, right? So if I kick it, it's going to go flying because it doesn't have a large mass and it can't resist my change in motion very well. Does that make sense?
Yeah.
So that means if I, so this is really cool because we could use this in many examples, but that's Newton's first law. Newton's second law says F equals M times A. And let's break that down. F stands for
Force equals mass times acceleration.
Yeah, exactly. So let's say I have, and this kind of goes back to Newton's first law, because let's say F equals ma, right? What happens if my force is 0? What's my acceleration?
If your force is 0, what is your acceleration? 0.
Yeah, and that goes back to Newton's first law, right? Because an object will stay at rest or an object will stay at motion unless acted upon by an outside force, right?
Yeah.
So there's no change in acceleration unless there's a force. So in the case of a car, let's say I drive this car on a highway and I get it to 60 miles per hour, and then I take my foot off the pedal. It's going to slow down over time, right? Because of air resistance and friction between the tires and the floor. They're going to rub against each other. The air is going to keep on pushing against the car. So it's going to slow it down until it hits 0. Notice in the up and down direction, the two forces are equal. Gravity is equal to the force of the road pushing against the car, which is weird. We'll talk about that more in a second. But basically, that's why the car isn't just going to fall down into Earth's surface, right? Because there's a force pushing it upwards with equal size as the force pushing you down. Does that make sense?
Yeah.
So F equals ma. So let's say I had a mass of 1 kilogram and I had an acceleration of 5 meters per second squared. So 1 and 5. What's my force going to be then? My mass is
1
1,
and 5.
acceleration is 5. What's my force?
So what?
So my mass is 1 kilogram
Yeah.
and my acceleration is 5 meters per second squared. What's my force?
Then that's 5.
Yeah.
The force is
Because
5.
exactly, the force is 5, and the units that we use is called literally just a newton. So 5 newtons of force.
5 Isaac Newtons.
Yeah, 5 Isaac newtons. So basically, force is equal to mass times acceleration. So you can see here, if I have a large force and a small mass, I will have a large acceleration, which makes sense. If a large force and a large mass, the accelerations can be very small. And we'll look at, I'll show you guys a simulation later. But F equals ma. So in the case of here, we have 2 people pushing a cart versus 1 person pushing a cart. When 2 people are pushing, you have more force. which means that this guy will go faster over time because he will accelerate faster. Now, if only one person's pushing, I have less force, which means that I accelerate less, right?
Yeah.
And the last law is called action and reaction, which is a very cool thing because basically it says for every action, there's an equal reaction of equal strength in the opposite direction. So let's break that down a little bit. If I punch a wall, basically that's saying the wall will punch me back with the same force.
Which is stupid because like you'd never think of a wall punching you.
Yeah, it's not literally punching me, but it's basically saying if I put a force into a wall, why is it
And
going to
it
hurt me?
exerts the equal force.
Yeah, it exerts an equal force back on me.
So technically, wait, but that means if I kill someone, will I die?
No, that's different. But like, let's say us right now, why are we like, we know gravity's trying to pull us to the center of Earth's core, right?
Yeah.
So why are we not falling down onto Earth's core right now?
Because there's some like area. Like there's like more like this much area in between.
Yeah, but what's keeping us up right now?
The surface of the earth.
Surface of the Earth. So basically, in this case, it's using Newton's third law again, is gravity's trying to pull us down to the Earth, right? This is our weight. If you go on a scale, it's reading our weight. Basically, gravity's pulling us down, but what's pushing us up is an equal and opposite direction force called the normal force. The normal force is basically what keeps everything upwards. Basically, if something's on a surface, this is keeping us here because the normal force is pushing us upwards. So basically, if gravity is pushing us downwards, the road that's supporting us upwards is going to be in the opposite direction. That's why we're not moving anywhere up and down, right? We're just staying here. If we were to move up and down, that means these forces are unbalanced. In this case, they're balanced. So that's basically this is Newton's third law of motion. So also in this case, let's say I was on a boat and I started walking forwards. Because I'm walking forwards and that's pushing me forwards, the boat's going to start pushing backwards, right? So don't do that. Let's say it's the same thing on a skateboard. You start walking on a skateboard, the skateboard's going to kind of slip under you, right? Because the skateboard also is going to move in the opposite direction in a force. So these are Newton's three laws. First law says that object at rest will remain at rest unless acted upon by an outside force. That's why everything that around you right now is not moving because there's no forces acting upon it, unbalanced. So that's also another thing. There are forces acting upon everything in your room right now, right? That's gravity. And then what's keeping it up is the normal force. So they're balanced. But in the case of, let's say I kick something or I move something with my hand, I'm putting an unbalanced force here and moving it. But also, if an object is in motion, it will continue to be in motion, just like the Voyager that we talked about, unless acted upon by an outside or unbalanced force. In the case of the Voyager, it's in space. There's no forces really acting upon it, so it's going to just keep on moving really fast. In the case on Earth, things are going to slow it down. Friction, air resistance, stuff like that. Second law just says F equals ma, which is how we calculate things. Third law says every action, there's an equal reaction of opposite direction. Cool. So falling objects accelerate as they fall down, right? What does that mean? It means that their speed increases as they're falling down. So basically, I drop something. First, its speed is 0. Then it's going to start speeding up and speeding up and speeding up. So the acceleration that we use on Earth is basically 10 meters per second squared. That means if I drop something really, really high up, and assuming there's, let's say, assuming it's in a vacuum, right? Basically where there's no air. If I drop it, it's going to start speeding up 10 meters per second every second. So after 1 second, what's the speed? How, Chen? After 1 second, how fast is this thing that I'm dropping going to be? So at 0 seconds, let's say it's a ball. I drop it off the Empire State Building, and assuming there's no air here. 0 seconds, the speed is 0. After 1 second, how fast is that ball going to be moving?
I think I'll be moving faster.
It won't be moving faster.
Well, you need to. I think you need. Wait. I think I'll be moving at 1 mile per hour.
Or in this case, it's going to be moving 10 meters per second.
Okay.
After 2 seconds, how fast do you think it's going to be moving?
20. 20.
Yeah, 20. 3
After
seconds.
1,000 seconds, it'll be 2,000 seconds.
After 1,000 seconds, it'll be 10,000.
2,000 miles per hour.
After yeah. Well, basically you just multiply it by 10. So every second, everything speeds up 10 meters per second. So, and we could use this to calculate a lot of cool stuff, but we're not going to do that in this class because, that's more math based. And this is kind of just looking at the concepts. But yeah, so things speed up as they fall towards the earth. And two different objects falling at the same speed, let's say. So this is actually a really cool concept. And this goes back to our first question was, in a vacuum, I drop a bowling ball and a piece of paper at the same exact time, at the same height. I drop it, and what happens? It turns out that these objects will fall at the same exact speed in a vacuum, right? This isn't in a real air situation. So in a vacuum, they're going to fall at the same exact speed, which means that they're actually going to hit the ground at the same exact time. This doesn't actually happen in real life, though, because why? We have air resistance, right? Larger surface areas will feel more air resistance. That's why if I drop a piece of paper, it's going to take a very, very long time for it to fall to the ground, right? Because there's a lot of air slowing it down. But let's say there was no air, that paper will drop the same exact speed as anything else that I'll drop in a vacuum. So if gravity points downwards, which way does air resistance point?
Upwards?
Yeah. Gravity's gonna pull it downwards, air resistance pushing it upwards. So papers fall so slowly because, well, there's so much air resistance, right? There's so much surface area compared to its mass, which is very little. It doesn't really have much mass. It doesn't weigh very much.
So if the paper was very heavy, would it fall faster?
In a real life situation, or are you talking about in a vacuum? Because everything
in a real life
falls
situation.
In a real life situation, yeah. Think about, let's take, instead of a piece of paper, we said a book with the same surface area, right? Let's say this book right here. It has the same surface area as a piece of paper, but it has much more mass. So it's gonna just cannot fall much faster than one piece of paper, right? Very, very good question. So what about on the moon? Is there air on the moon?
No.
No. So this is exactly where we can conduct this experiment, right? So the first one of the Apollo missions, Apollo mission 15, 1971, we will see what happens. Show my sound.
Penetrometer drum in the ETB.
Not quite yet. I haven't put the solar wind in yet, but I will. Shortly. I want to watch this. I have a good picture there. I've got
Beautiful picture, Dave.
Well, in my left hand I have a feather. In my right hand a hammer. And I guess one of the reasons we got here today was because of a gentleman named Galileo a long time ago who made a rather significant discovery about falling objects in gravity fields. And we thought that where would be a better place to confirm his findings than on the moon. And so we thought we'd try it here for you. The feather happens to be appropriately a falcon feather for our falcon. And I'll drop the two of them here, and hopefully they'll hit the ground at the same time. How about that?
How about
Which proves that Mr. Galileo was correct in his findings.
Cool, right? So basically, this is saying that if there is no air, things will fall at the same exact speed for all objects. Now we know that's not true.
So like if you have this 1 billion ton object,
Yeah.
that is definitely gonna weigh down the moon though. And you drop it on like the same surface as a feather, it's gonna drop at the same speed.
Assuming that the moon, okay, 1 billion tons. 1 billion tons is,
Yeah, and let's say the moon weighed more than 1 billion tons, so it didn't get weighed down.
oh, okay, yeah, then they'll fall at the same exact speed.
Okay.
Cool, right? So at least that's something that we can say. So what does that have to do with everything else that we learned about today? So Newton's third law. So basically, every action there's an equal and opposite reaction. F equals ma. We could use that for a lot of cool topics, like once we're able to draw these things called a free body diagram, basically looking at all the forces acting upon an object, we can start calculating its acceleration very easily. And then that's how we can go, like using rockets and stuff like that. We have to calculate how much booster we have, what's the mass of that entire rocket, and what the acceleration is for that rocket. This is all important stuff for astronauts and, you know, physicists and stuff like that. So
The people who build what astronauts go in.
yeah, exactly. Engineers, stuff like that. They all have to use this all the time to calculate how much fuel they need and stuff like that.
Or else something bad will happen.
Or else, yeah, exactly. They won't have enough fuel, for example. And Newton's first law is, again, objects at rest will remain at rest unless acted upon by an outside force. Objects in motion will continue with constant speed and direction unless acted upon by an outside force. So those are the forces that we talked about. Cool examples. So this is these are some cool, I guess, like critical thinking things that we can talk about. One being, if I shot a gun completely horizontal, so I shot a gun horizontal, let's say it's a very, very infinitely flat field, right? With no air resistance. And I drop a ball at the same time that I shoot a gun. Which one will hit the ground first?
The ball.
Okay, ball. What do you think, Hao Chen?
I also think it's the ball.
Okay, ball. So turns out, another trick question, they all will both hit the ground at the same time.
Well, if like you didn't say fireball it down, you said like I thought you said fire it like straight. Then it would keep going this direction while the ball would go this direction.
Right. So, yeah, you're completely right on that. It's not like they're gonna hit the same piece of ground, right? That bullet is actually gonna hit much, much farther. But it turns out because what is the only force pulling both of these things to the surface?
Gravity.
And what do we
What
say
if
about
there
gravity
is no
on
surface?
what?
What if there is no surface?
Oh, just hit into whatever. Well, if there's no surface, there's no gravity, right? So
Yeah, but what if
unless you're
there is
talking
no
about a black
gravity?
hole. What?
What if there's no gravity?
Then nothing will fall.
Okay.
So it's weird, right? Because obviously they're not going to hit the same place, but because the only force that's acting upon both of these objects is gravity, and we said that gravity on free-falling objects will all fall at the same exact speed, they will actually both hit the ground at the same exact time, assuming there's no air resistance, right? If there's air resistance, well then, you know, a lot of new things will be added in. but we're just looking at it without air resistance. So basically, it just means that you can see here, right? Even if it had a speed horizontally, not Siri.
I didn't get.
Um, if there's a speed in the horizontal direction, which is true for the bullet, right? Because the bullet is actually moving horizontally. Well, that doesn't really matter which way it's moving horizontally, because at the same time, the only force that's acting upon it is gravity, which means that it'll pull it down at the same exact speed as that ball that we talked about. And so you can see here, right? Let's say this is the bullet, and the bullet is also going to drop down and hit the ground at some point. At every single second, let's say this is 1 second, you can see here it's at the same exact height, right? 2 seconds, same exact height. 3 seconds, same exact height. And notice how, let's say 3, 2, 1, right? 1 seconds, 2 seconds, 3 seconds. Notice how the distance that it covers is faster and faster. Why is that?
The distance that it covers is faster and faster because every time you add 10.
Right. Every single second, you'll add 10 meters per second. So it means that the only thing that's constantly moving up is speed. So that means the distance it covers is actually exponential, which means that it actually increases over time, which is, weird, but we can talk about that. So basically, this also has to do with, you do some calculations, and basically you come to the conclusion that, let's say I throw a football, right? How will I actually maximize my distance if I throw it with the same exact speed every single time? If I throw it with the same exact speed every single time, turns out 45 degrees is actually the most I can use to actually throw the farthest.
45 degrees is exactly diagonal.
Exactly. It's exactly diagonal. So that's actually how I throw the farthest. And that's because I maximize the X and the Y, kind of. X being horizontal, Y being vertical. Because, well, if I throw it straight up, it's gonna be in the air the longest, right? Because actually it's gonna go very high, but it's not gonna have a lot of forward momentum, so it's not really going anywhere. If I throw it straight down, well, it's not gonna be in the air very long, so it's actually gonna hit the ground pretty fast. So the best, medium in between it is 45 degrees. So what happens if something in traveling in space, let's say the Voyager, right? So what happens if, assuming there's no collisions?
It will just keep going.
It'll just keep on going, right? There's no force acting upon it, and Newton's first law says that, well, I think traveling in motion will continue
Well,
traveling.
there is a bit of gravity.
There's a little bit of gravity, that's true. I mean, everything in space is actually technically pulling on us, right? Which is very, very small. Infinitely small, actually. What falls faster, something on a 45-degree ramp or a 60-degree ramp? That's a interesting question.
I don't know.
So let's say I have a ball and I was trying to roll it down a ramp. Would I want a 45 or a 60-degree ramp to make it fall faster?
45?
Well, let's think about it. Or let's say like 13 degrees, like a very small amount like this, if I drop it, it's going to go downwards. Or if I have like this and drop it and go just downwards, which one will go faster? How, Chen, you want to give a guess?
I think the 60-degree ramp.
Okay, and why?
Because it's more tilted.
It's more tilted, which means actually it has more gravity pulling it downwards. Oh, sorry, more of a component of gravity pulling it downwards. Let's say we're at horizontal, right? Gravity's still pulling it downwards, but what's pushing it upwards again?
Normal force.
The normal force, which basically is just, it's basically just a reaction, right? We said like the whole Newton's third law is action reaction. It's just a reaction. But at 45 degrees, gravity's still pulling down the same exact force. But notice how, because at 45 degrees, the normal force is still pushing upwards, right? I mean, it's actually pushing 45 degrees, so it's gonna be like this. pushing it that way, which means that there's actually less, at least still a lot of normal force keeping it up. So it's actually going to fall slower. 60 degrees though, there's less normal force, right? Pushing it upwards, which means that actually it will fall faster. So yeah, why does a bowling ball knock over pins using Newton's laws of motion? Why does a bowling ball knock over pins?
Because an unbalanced force is acting on it.
Yeah, the bowling ball is gonna knock. Oh, but okay, but what happens if I rolled a piece of paper at the pins? Why won't that knock it over?
Because air resistance.
I guess,
So
but I mean,
unbalanced
let's
force.
say at the same speed, I rolled a crumpled piece of paper versus a bowling ball at these pins. Why does the bowling ball knock them over, but not the crumpled piece of paper?
Because the crumpled piece of paper doesn't have more. The bowling ball has more mass.
More mass, which means it has more what? Remember that I word?
Acceleration.
It doesn't have more acceleration, but it has more what? Newton's first law. Remember that word that starts with I?
Wait. What?
It starts with an I. It has more
Inertia.
inertia. Awesome. So if we go back to Newton's first law here, inertia is an object's ability to resist change. So the larger the mass, the larger the inertia, which actually means that it basically has more mass, right? Which means that it can knock those pins over, which has less mass. In the case of a crumpled piece of paper, that crumpled piece of paper doesn't really have much mass, so it can't really push over those pins. Would something on the moon fall faster than something on Earth? Okay, so this is interesting, and then we're gonna go over it.
No, because the Earth exerts more gravity.
Yeah, and why is that?
Because Earth has more mass
than the moon. Yeah.
Yeah.
So what does that mean in the acceleration?
It depends on your mass.
Not really, but what can we say about acceleration on Earth compared to the moon? Things accelerate faster or slower on the Earth compared to the moon?
I don't know.
Hachan? Do you think things will accelerate faster or slower on Earth compared to the moon?
I think things on Earth would accelerate slower.
Well, so this is actually I'll give you guys a hint. Newton's second law says what? It's that equation. Remember that equation?
Newton's second law says
F equals
force equals mass times acceleration.
Right. So we said there's more gravity on Earth than the moon, right? Because it has more mass.
Yeah.
So let's say we use the same exact object with the same mass, so we don't have to care about the mass part of it. So more gravity means there's more force, right? Which means there's more acceleration. So Earth will accelerate faster than the moon. And we saw with that video, right? With the Apollo mission, when they dropped the hammer and the feather, they actually fell pretty slow, right?
Yeah.
So let's compare Earth to Jupiter now. Which one has more mass? Earth or Jupiter?
Jupiter.
Jupiter. So on Jupiter, that means things will accelerate faster or slower?
Faster.
Faster, much faster. And we can look actually at the acceleration of different planets. So on Jupiter, things will accelerate at 26 meters per second squared. So almost 3 times the speed, almost 3 times the I guess overall acceleration that Earth has. Earth is 9.81, but we say 10, much easier. The moon is 1.62, so maybe like 20% of what Earth has. Cool, right? So this is actually based off of their actual sizes. And we can actually calculate this, and I'll show you this on the next slide. This is a gravitational force equation. You don't need to know this, obviously, right? But it's kind of just cool to look where does this all come from. So this is F of G. F of G just means the force of gravity equals big G, which is just a constant. It actually doesn't matter. So let's get rid of that G. Mass 1 times mass 2 over R squared. Mass 1 is, let's say, the gravitational pull between Hao Chen and Ray Chen. The mass of 1 and mass of 2 is probably going to be around the same, right? You guys are the same age and stuff. So you guys will probably have the same mass. So let's double. So let's say it's, I don't know. Do you guys know how much you weigh?
Like 70.
70 pounds. So that'd be like 30 kilograms. Let me just divide by 2. So 30 times 30. What's the distance between you guys?
What do you mean?
Like what? How far are you guys away from each other?
I have no idea.
Okay. Well, it's probably pretty, let's say like 5-10 meters, something like that. But notice G over here is 6.674 times 10 to the negative 11. So basically the force between you guys are very, very small, right? The gravitational force between you guys. Doesn't mean it's 0, but it means it's just very, very small. So let's say you guys increase the distance between each other. If you increase the distance between each other, do you think the gravitational force will increase or decrease?
If you increase the distance,
Yeah. Will that number be smaller or bigger?
like we go further or closer,
Farther away from each other.
then the gravitational pull gets smaller.
Yeah, exactly. So let's talk about like the Earth and the Sun, for example. If the Earth was closer to the Sun, well, the gravitational pull would be much stronger, right? So these are cool things that we talk about regarding gravitational force, and you can use this to calculate force between anything, to be honest. And this is a really cool thing. Okay, cool. So for the last 5 minutes, and I can send this to you guys too, so you guys can play around with it, is these cool gravitational force labs that we can do. So basically in this case, let's say mass 1, right? So you can hear here, the forces between these increases when I go closer. It's kind of weird actually, I'm thinking about it. So in this case, let's say mass 1 is very small. Where is the blue or red balls? Where are they going to move?
The blue is gonna move to the red, and the red's gonna stay.
Well, actually, the red's going to also move towards the blue, but which
Yeah,
one's going to move
but just-
faster?
Yeah.
Yeah, the blue is actually going to move much faster to the red. The red is going to move very slowly. And look, notice how the force from the red to the blue is this, and the force from the blue to the red is also this. They have equal forces, right? What Newton's law does that have to do with?
The first.
What says for every action there's an equal and opposite reaction?
Oh, the third.
Yeah, which means that in this case, if there's a action like this, the reaction is the exact opposite, which means that they actually have the same exact forces on each other. They come in the same exact thing. But notice how mass 1 is, let's say, 10 kilograms and mass 2 is 1,000 kilograms. What law says that mass 1 will accelerate faster than mass 2? This is the equation law, remember? What says F equals ma? Where
Force F equals ma. The second.
Yeah, exactly. And so basically, let's say the force is the same. The force is the same between the blue and the red balls, right? But mass 1 is much smaller. The blue ball is much smaller than the red ball, which means that the blue ball will accelerate much faster, right? Because let's say force equals 100 and mass in the blue ball is 10. So acceleration is what?
Acceleration.
If force equals 10 and blue ball mass is 10, what's acceleration? F equals ma. And obviously this is kind of
what's the mass of the blue ball?
10.
And the red ball?
We're just looking at the blue ball, how fast the blue ball is going to accelerate.
And then what's the acceleration. No, what's the acceleration of the blue ball?
Yeah, so that's what I'm asking, right? So if I showed you a little, I don't know, this is way above your guys' math. Oh, it's not actually, but we say F equals MA, right?
Yeah.
M times A. So we're finding A in this case. A will equal what?
A
F
equals
over M, right?
Mhm.
And we said F equals 10 and mass equals 10. So acceleration, oh, my bad. What did I say force was? 100, right? So 100 over 10 equals 10.
100 divided by 10 equals 10.
Awesome. And then the red ball, no, let's actually use the red. Acceleration equals 100 still, right? Because we said the force is the same, but the mass is much larger. I think actually the mass for this one was 1,000. So what's going to be the acceleration? 100 divided by 1,000.
100 divided by 1,000. I have no idea because I don't know this.
Well, it's just 0.1, right?
Oh.
Well, it's the same thing as like 1 divided by 10.
Okay.
So you get a tenth. So you can see here the acceleration of the two things. The blue ball is going to move much faster than the red ball because, well, the blue ball also has less inertia, right? So it kind of resists that motion much less than the red ball. Okay, that one's confusing. I get it. So we're going to go to a more interesting one for the last minute. And you guys can look at these later on too. So it's the one that I wanted to show. Okay, besides the point, I can show you projectile motion. Basically, and I can send you guys a link so you guys can actually do this. Well, like play around with that if you want to. Well, basically, I don't need intro. Basically, you're trying to hit this target, right? And you, I guess you shoot a cannon. So you have to actually look at oh, see like that. Oh, that was perfect. Oh, never mind. So you'd have to move it around to actually, oh, that was too much. So like what? Okay, that's gonna hit. There we go. Yay. So it depends on your initial speed. If I increase the speed, notice how it's gonna move much farther away. So these are just cool things that you can play with. And notice how the mass, a change of mass, what's gonna happen? Absolutely nothing, right?
Yeah.
Because if I have this first same exact speed, it doesn't actually matter. If I could change the gravity, so let's say this is Jupiter instead, it might have worked. But yeah, okay. Other than that, that's really it for me. You guys can play around with that. But also, I know that the physics that I taught today is a lot harder than what you're normally used to in fourth grade or third grade even. So let me know if you have any questions. You can read through these slideshows, PowerPoints on the Google Classroom. I posted all of them. But other than that, I will see you guys on Monday. Have a great weekend. Go enjoy your summer as usual. So yeah, let me know if you have any questions. But other than that, I'll see you guys on Monday. All right.
Okay.
All right. See you guys. See you, Hao Chen. See you, Ray Chen.
Bye.
Thanks
Bye.
for being great students. Goodbye.